Hi friends, in this video we are going to discuss about parallel operation of DC generators. We know that generally the parallel operation for generators and transformer, not for motors, right? So what are the advantages of parallel operation? One is the continuity and reliability and load capacity increases and efficiency increases. Like that, many advantages are there for parallel operation. What are the conditions for parallel operation of DC generators? Not for synchronous generator, not for transformer, for DC generator. Here the first one is polarity. Polarity should be same. Sir, if the polarity not same, what happens, sir? If the polarity not same, it will show that dead short circuits. Must and should. Dead short circuits will take place. Be careful. Maintain the same polarity for parallel operation. And next one, second one, terminal voltage. This is also must and should be same. Sir, if the terminal voltage is not same, what happens, sir? Circulating currents increases, losses increases, efficiency decreases, and one generator may get overloaded or underloaded. Whatever it may be overloaded or underloaded, which damages the machine. Like that, many disadvantages are there. If terminal voltages are not same, we should maintain the terminal voltage same and polarity also same. Next one. In generally, for example, this is DC positive and negative. I am going to add two generators in parallel. One is already existing generator, next one is the incoming generator. At this case, the incoming generator during the parallel operation or before parallel operation, when we are connecting parallel operation, at this condition, incoming generator excitation should be increased and existing generator excitation should be decreased. During the parallel operation, the incoming generator excitation should increase and already existing generator excitation should be decreased. Then only we can get the same or constant terminal voltage. Then when the same terminal voltage, then we have to add in parallel operation. That is the first condition we have to do during the parallel operation. And when we are removing the generator from the parallel operation, at this condition, the removing generator excitation should be decreased and already existing generator excitation should be increased. Existing generator excitation should increase and removing generator excitation we have to reduce up to floating point. Floating point nothing but the terminal voltage is equals to bus bar voltage, nothing but the same voltage up to that condition. Actually, at this condition, there is no delivering of power, and no absorbing of power from the bus bar or from the generator. Floating point, same voltage. There is no flow of current. So just remember this. Removing generator excitation should be decreased and existing generator excitation should be increased up to floating point. At that condition, remove the generator what you want to removable. Are you getting or not? So here two condition during the parallel operation, during the removing. You have to observe these two. And in generally, if you draw the speed characteristics, generally, how actually for shunt motor the speed characteristics are like this, and for tell me, and for differential compound motor speed characteristics are like this. Yes or no? Yes or no? And this is for motor, whereas go for generator when this is load and this is the voltage V. How the characteristics actually for series generator the characteristics are like this. For over compound generator characteristics are like this, but the shunt and under compound and differential compound the characteristics are like this. So the voltage characteristics for shunt and under compound, shunt and differential compound. So here the important thing is that which are having rising characteristics and which are having drooping characteristics. That is important. Let's see, this is the current and this is the voltage. Actually under compound is like this. Of course separately excited is like this. Shunt is like this. Differential compound is like this. Whereas series generator is like this. Over compound is like this. During the parallel operation, we must take a caution is that the generators which having the drooping characteristics, these are eligible for parallel operation. These are not eligible for parallel operation. Generally, the series generator and over compound generators are not preferable for parallel operation. In generally, shunt generator is more preferable, as well as under compound and differential compound also no problem, which having the drooping characteristics, that is perfect for parallel operation. Sir, in series generator, how we can get the parallel operation? By equalizer rings or connecting wires, equipotential connecting wires. By using that equalizer rings, for example, like these generators are there, so by connecting the equalizer rings, we can make it in parallel, but this is difficult thing. But for shunt generators, no need to equalizer rings, no need of equipotential points, we can connect directly. So in series generator, by using equalizer rings or equipotential connecting wires, we may make it in parallel. So you should remember that drooping characteristics are must for parallel operation. Is it okay? So let's see the different conditions in parallel operation. How we can get the parallel operation for different conditions. What are the features for the different conditions? They will give you the drooping characteristics actually. So let's see. Let's see here. I'm going to draw the some different cases. In first case, same no load voltage and same no load voltage and different drooping characteristics, different drooping characteristics. See how, for example, this is the load current or current and this is voltage. I said that same no load voltage for E1 and E2, two generators, but this is the first generator and this is the second generator, G1 and G2. For example, this is my terminal voltage or bus bar voltage, my bus bar voltage. So what is the condition here? Same no load voltage and different drooping characteristics. The bus bar voltage is less than no load voltage. This is the condition. At this condition, in generally, the drooping is directly proportional to are inversely proportional to, they will ask you question like that. Are you getting or not? See here, when the generator 1 is more drooping, which is more drooping, that is less rating. The drooping is inversely proportional to rating. If the more drooping, that is less rating. If it is less drooping, that is more rating. So here the generator 1 sharing the current of IL1 and generator 2, the load current is IL2. Nothing but here, which is more drooping, that is less sharing. Which is the more drooping, that generator having less sharing, and which is less drooping, that generator is having more sharing. So the drooping is inversely proportional to sharing. Are you okay or not? So be careful. In this condition, the generator 1 is less sharing, and generator 2 is more sharing, right? So now the second condition is that different no load voltages and different drooping characteristics. What is that? Different no load voltages and different drooping characteristics. Okay, let's see how it is. For example, see clearly, this is the line current, this is the voltage, different no load voltages. For example, this is the E1 and generator 1, this is the E2 and generator 2. So different no load voltages and different drooping characteristics. I am taking here bus bar voltage is equals to equipotential point or equisharing point. Equal sharing point, both are same. Nothing but my bus bar voltage is this one. This is the first case. Different no load voltages, different drooping characteristics, and my condition is if the bus bar voltage is equals to equal sharing point, equal sharing voltage. And next taking the same, listen carefully, different characteristics. This is IL and this is V. Again same, for example, this is E1 and this is E2, where this is my generator 1, this is my generator 2, this is the equisharing point. My bus bar voltage is, this is my bus bar voltage. My bus bar voltage is greater than equisharing point. Are you okay? Bus bar voltage is greater than equisharing point, but bus bar voltage is less than no load voltages. No load voltages. This is the another one. So now I am discussing about these two factors, how it is. Okay, I know that already. The drooping is inversely proportional to rating. Yes or no? Drooping is inversely proportional to rating. See here generator 1 and generator 2 sharing the same load. In this case, generator 1 and generator 2 sharing the same load. There is no any difference between two generators. But here generator 1 is, which is the generator 1 is more drooping, nothing but less rating. Yes or no? So here generator 2 is less drooping, nothing but more rating. Yes or no? I said you already, drooping is inversely proportional to rating. Here generator 1 more drooping, so less rating. Generator 2 less drooping, so more rating. So here generator 1, generator 2 are having the different ratings but sharing the same load. Nothing but ultimately generator 1 is more rating, more drooping, nothing but less rating sharing the same load. So this is the overloaded generator. And this having actually more rating but sharing the same load. So generator 2 is underloaded. This is a very important thing. In generally, this is not preferable. The first one is preferable, no problem. The first point, which having less rating, that is more drooping, sharing the less load. Which having less drooping, nothing but more rating, sharing the more load. In first case there is no any problem, but in second case there is a problem, which is more drooping, nothing but less rating is overloaded, which is less drooping, nothing but more rating is underloaded. This is the problem with this condition. Let's go to this condition. At this condition, see here, this is the bus bar voltage, this is the equipotential point, and this is I2, the load sharing of the second generator, and this is I1, the load sharing of the first generator. See here, generator 1 is the more drooping. Yes or no? Generator 1 is the more drooping. Nothing but less rating. Yes or no? Less rating. This less rating is more load sharing. More load sharing, which is very difficult. This is very overloaded. Very overloaded. Yes or no? See, this is more drooping, nothing but less rating. But the current sharing is more. That's why this is overloaded. Whereas the generator 2, which is less drooping, then more rating, which having less drooping, that is more rating, nothing but see here, generator 2 less load sharing. So this is more rating, less load sharing. So this is very underloaded. So this is also not recommended. This is also not recommended. B also not recommended. So let's see for C. So the third one. See here, ma. Is it okay? This is V and this is IL. So different no load voltages and different load sharing. Different no load voltages as well as different load sharing. See, for example, this is E2. Where is my generator 1? This is my generator 1 and this is my generator 2. This is the equi-sharing point. For example, this is my bus bar voltage. Bus bar voltage. Again here, see here, what is that? The bus bar voltage is less than equi-sharing point. This is the case 3, C, A, B, C, third case. At this condition, again, generator 1, more drooping, nothing but less rating. Of course, less rating, and as well as the current is sharing, or the sharing also less. Less sharing, less load sharing, no problem with generator 1. And what about next? Generator 2 is a less drooping, which is less drooping, more rating machine is less drooping. Of course, the load sharing also more load sharing. Yes or no? More load sharing. So no problem with this one. Actually, this is not good, but this is bad. This is not good. Somewhat overloaded, somewhat less underloaded. Not not good. But this is bad because more overloaded, more underloaded. This is not bad. We can use because the generator one which having less rating, less load sharing, which having more rating, more load sharing. This is 100% we can use. Okay, so A, B, C is completed. The special case, I'm going to tell you the special case D. What is the D? For example, I will take here the special case D. Let's see what is the case D. Here, my case D is that if the bus bar voltage is greater than the equipotential point or equi-sharing point, greater than equi-sharing point, and in between no load voltages. No load voltages. This is very different one. What I am telling is that the bus bar voltage is, let's take here, I will redraw clearly. See here, for example, this y-axis is V, x-axis is IL. For example, this is my generator 1, which is E1, and this is my generator 2, which is E2. Actually, equi-sharing point is here. But I said you, my bus bar voltage greater than equi-sharing point. Sir, greater than nothing but can I take here or here or here? Again, I will give you an condition in between the no load voltages. We have two no load voltages, so we have to take in between. This is my bus bar voltage. Very different, right? Yes or no? So let's take here. See, this is the generator 1 sharing I1. Where is my generator 2 sharing? So this is the generator 2 sharing is I2. What is this, sir? On reverse direction. What is this? Yeah, sir. This is the positive, but this is the negative. Negative current. Positive current nothing but which delivering the current. Negative current nothing but which observing the current. This is very dangerous case because here the generator 1 which is more drooping, which is less rating, more drooping nothing but less rating, is sharing the load of I1, but take the generator 2 which is less drooping nothing but which is the more rating, but which is, this is I1 delivering by generator 1, but this is minus I2. Minus I2 is nothing but observing the current. Observing is nothing but the motor, delivering nothing but the generator. The machine 1 act as a generator, machine 2 act as a motor. Sir, it is delivering, okay. Sir, how it is observing? Because it is delivering, that current is observing. Some part of the current is observed by this motor. So, here the load of the generator is equals to actual load plus motor load. actual load and motor load. Nothing but the generator have to deliver the load or power to the load and for the motor. Actually, we have some load and motor is another burden to my generator. So here my generator is very overloaded. This is very dangerous condition. Don't operate two DC generator like this. This is very dangerous condition. These are the different conditions in parallel operation of DC generators. In first case, same no load voltages, different drooping characteristics, and the bus bar voltage is less than the equi-sharing point. Thus is perfect parallel operation. If the no load voltages are not same, we can operate in four different models in parallel operation. One is equi-sharing point equal, second one is greater than equi-sharing point but less than no load voltages, next one less than equi-sharing point, and next one greater than equi-sharing point in between two no load voltages. These are the different possibilities to operate in parallel of DC generators. So once quick review. What is that? Generally, due to parallel operation, we can improve the load capacity, reliability increases, continuity increases, and efficiency increases. These are the advantages. Then generally, which having the drooping characteristics eligible for parallel operation like a shunt, under compound, differential compound, but more preferable is the shunt generator. Over compound and series generator having the rising characteristics which are not preferable for parallel operation. But in series generators, by using the what equalizer rings or equipotential connecting wire, we can make it in parallel. During the parallel operation, the excitation of the incoming generator should be high and exciting generator excitation should be less in order to maintain constant terminal voltage. Here the conditions are that polarity should be same, terminal voltage should be same. If the polarity not same, it will lead to dead short circuit. If the terminal voltage not same, it leads to circulating currents increases, which is one overloaded, one underloaded, which losses increases, efficiency decreases, damage of the machines. And next one. When we want to remove one generator from the parallel operation, the excitation of the removing generator should be reduced and existing generator should be increased up to floating point. Floating point nothing but same voltage point. Then after we can remove that generator. And then after different characteristics you saw already. This is simply about the parallel operation of DC generators. Are you okay? Thank you.